I mentioned that dinosaurs' best EOD for preservation happens to be in rivers. And that's great. They're preserved in areas that rivers are flowing and depositing sediment. There's a bad part to that as well, in that rivers, what? It's moving water. If the water is moving, the sediment's moving. If the water and the sediments are moving, then the bones are also going to be moving. And so, as it says right there, after a dinosaur dies, it rarely just sits there and gets covered. Again, if a dinosaur just dies in the middle of anywhere and sits there, it's going to be completely destroyed by bacteria, fungi, all kinds of other things. If it falls into a river, it stands a good chance of preserving, but it's going to move. It's going to undergo what we call post-mortem or after death transport. And so this slide shows this. Right here, you've got a picture of this poor dinosaur that's died just recently. It fell into a stream. The stream is flowing like the arrows show, and it's washing along. Meanwhile, you have at the bottom of the stream a whole bunch of bones from some dinosaur that died a long time ago. And these bones are moving, bouncing around, grinding along the bottom, being deposited all over the place. So an organism might die in one spot, but its remains might be dispersed very, very far, very, very wide. And so it's a sad, sad statement, but it's probably the truest statement. We rarely ever find complete skeletons of any single individual dinosaurs. Typically, we find big dumped piles of bones and then have to reconstruct them. And why that is because of this fact that these river systems typically are moving them. So let's say a dinosaur dies. You're expecting to see there a body with a skull, there's the vertebrae, there's the arms, there's the limb, there's the tailbone. Sometimes we have it, but mostly we find situations like this. This is an actual sketch of a what we call a bone bed. You've got a scale at the bottom here. Let's say this is a couple of feet across, and here's a bunch of bones, and you see bones of every size, every shape, every distinction, all over the place. And this probably comes from many, many dinosaurs dying all over the place, and these bones being washed together. So it would be nice to have fully complete skeletons ready and waiting for us, but really, this is the mess we get. And so it's been said before that dinosaur paleontologists are really garbage collectors. They are. They're like sifting through a bunch of old bones and garbage to try to reconstruct something good. You can still get something for this as well. If we go back to this, let's imagine that all these different bones are dumped into this stream system. Well, think about it. There's a leg bone, there's a shoulder bone, here's part of an ankle, skull bones. You've got bones of every different size and shape, and they're going to behave differently in the stream as they're moving downstream. And so we talk about what's called post-mortem transport. I'm going to go through this exercise, and it's going to look very quantitative and math-oriented, and it is, but I'm going to break it down for you into sort of knowing the generalities. So you won't be doing any math on the exam or anything like that, but you'll have to in general know different aspects of how bones are going to be transported, where they're going to go. And so we need to look at the size and the shape of the bones. So S is the shape, that's sort of a generic term. And we can say that that is the area, the surface area of the bone divided by the volume. And so for a perfect sphere, a basketball, the area is 4 pi r squared, the volume is 4/3 pi r cubed. So if you had a perfect sphere, radius of 5 centimeters, again, multiply all that out, you'd get a number like that. Any bone or particle that deviates from a perfect sphere is going to have a higher AV number. So it means it's going to have a higher surface area per volume. So think about it. That example I gave right there is for a basketball, but a bone doesn't look anything like a basketball. Think of your arm bone. It's long. It has a long radius. It's thin. It's very, very different. And so anything that deviates from that is going to have a higher number. So you've got a bunch of bones that are going to be sort of sphere-like, and then you're going to have bones that get higher and higher numbers. Okay. Uh, we relate these things here. So in general, a higher area to volume ratio gets carried easier. A frisbee. A frisbee gets thrown easier or carries farther than a baseball. So a baseball is another one of those perfect spheres. It has a low AV, but a frisbee, high AV, can get carried farther. So if you have long flat bones in a river system, they are literally lifted and transported much farther, much longer than any round bones. So think about that. Bones that are like a frisbee, long and flat, are going to be moved much farther than bones that are more like a baseball, rounded. And we've defined 3 different bone transport groups. We have group 1. This has the highest AV or highest shape number system. These things move easily. You just have to have a little stream flow. As long as it's moving, they're going to start flying and circulating downstream. So ribs do this. The sternum, that's the breastbone. You don't need to worry. I didn't ask you to memorize that, but the scapula, the ulna, those things move easily. Group 2, these have a lower AV, but also sort of a medium density bone, and these are moved by moderate stream flows. So the river has to move a little bit faster to move these things. And these are most of the big bones that we find: femurs, tibias, humerus, radius, the bigger arm and leg bones, and then the pelvic girdle bones, and then finally the group 3 bones. They have the lowest AV. They're the closest to spheres, and then the highest density. They're dense and heavy, and they're going to not move unless you have high stream flows. These are things like the skulls, teeth, mandibles, so lower jaw, upper jaw, this type stuff. So you can look at any given bone bed like this and say, well, what is this? Is this a group 1 bed, a group 2 bed, a group 3 bed? And when I look at this, I see a lot. There's some big bones, big long bones, but I see lots of thin, small, long bones. These are bones that have flown down the stream like a frisbee, probably collected from many, many dinosaurs, tens of dinosaurs, perhaps even hundreds of different individuals, and they've moved a long way and been dumped somewhere else. So this would be an example of a group 1, almost a group 2 type bone bed. If you had a bone bed that had a bunch of skull bones and a bunch of teeth, it'd be something like here. And notice the selection of the bones can then tell you something about the environment, whether it's big, high moving, fast moving stream or a little thing that's slowly percolating along. We can also look at the bones and their orientations. So, and then we map out these things in what's called a Rose diagram here, like this, where you sort of lay a compass down and you have north, south, whatever, and you literally measure how the long axis of the bones are pointing, and we can indicate whether, oh, okay, these bones in this part of the river are pointing either up and down, basically either north and south, most of them. So that's where water is flowing. So bones that were deposited along here, they're all going to orient like this. And we know this actually because we can go to modern streams and dump a bunch of bones in there, or a bunch of little plastic objects or wooden objects or metal objects of particular shapes in a flowing stream, or put them in a flume in a laboratory, and you put them in every orientation with a little bit of flow, they all line up like this. This over here is called a crevasse splay. This is one of these situations where these meandering rivers spew out over the side, and then bones get scattered in every direction. So you'd have bones like this, where some are pointing north, south, some are pointing the opposite sort of direction, some are pointing east, west. It indicates ancient water flow. So these bones are very, very good at doing this. And this isn't trivial work. It takes a lot of work. Look at this mess. Go back to this bone bed. This is literally taking a compass and laying it along here, laying it along there, laying it along here, or taking, most of us have some type of iPhone or other smartphone, and they always have a compass app in there. You would lay the long end, for me it's an iPhone, lay the long end of your iPhone there on that one, and it tells you its relationship to north, to that one, to that one, to that one. This whole big mess can then be processed and say that, well, the majority of them are pointing sort of in this up and down, north and south direction, indicating that water flowed either from the top of the slide down or the bottom of the slide up. And then again, just to sort of put that back into perspective, here's the situation as it existed. Dinosaur dies, water's flowing, and it's going to leave series of bone beds like this all over the place. Again, this is the sad reality of most dinosaur paleontology. We don't have complete skeletons. We have highly mobile bones that we have to piece together.